Hello everyone, my name is Hasan Zerze and today I will talk more about special relativity, especially for position and time dilation. In my first video, I talked about length contraction, and let's go a little deeper and learn about the for position and the time dilation. Okay, in theory of special relativity, when we say for position, we talk about a vector with four entries, 2, 3, 4. And if you know, in three-dimensional Euclidean space, we define the positions with three entries, meaning that the x coordinate, y coordinate, z coordinate. But in the theory of relativity, we talk about four positions, and there are four entries. One is allocated to the time, so the time becomes our fourth dimension. So this, if you label them, this belongs to the time, and these three entries belongs to the three-dimensional position. Okay, and I think it's best to start with what the for position is for a rest object. If you have a rest object, any object like a stone or a book, this is object at rest. An object at rest will take the simplest form of the for position, and for the object at rest, the time ticks, but its position does not change with the frame of reference that is chosen. So for an object at rest, you choose the coordinate system in such a way that the object is not moving. Okay, so the object is not moving. The position of the object is not changing. It's only the time that's ticking. The time is ticking. There's a clock here, and time is ticking for the object. And suppose the time elapsing is, let's denote it by tau, the time ticking in the object's rest frame. And since the positions are not changing, we have 0, 0, 0 here. So this is the for position for an object at rest. Okay. Now, this is the simplest one, but you can actually, once you have this for the rest object, you can go from one reference state or reference frame to another reference frame to find out the for position in a different coordinate system. Say this is your object at rest, and this is the person, and then the person is measuring the time as the tau because it's in the same rest frame of the object. But then there's another frame. There is another person here, and then this frame is moving with a velocity of v. Okay, and then having a look at this object, this person, and trying to write down what the for position is for this object. And what we need to do is to transform this for position from the rest frame to the frame that actually moves with a velocity v with respect to the object. And we learned in the first video of this series that we make these Lorentz transformations. We apply it to this vector, and then what we get is gamma v, where gamma v was defined as 1 over square root of 1 minus v squared, and a matrix that will look something like this: v minus v minus v. We have shown this for one-dimensional motion, but you can generalize this for three-dimensional motion. And suppose that our object, or sorry, the reference frame v is moving along the plus x direction according to the object at rest. So these are 0. So what we're claiming is this Lorentz transformation will do nothing to the, well, it's going to do something to the y and z directions, but it doesn't have anything other than the, identity matrix here. Okay. And this is applied to the tau 0, 0, 0. And then what we get is gamma v. If you do the matrix multiplication, we get tau, we get negative v tau, and yeah, I think 0, 0. Okay, good. So this will be the new 4 position. So in general, with respect to a reference frame that moves with a velocity v, the 4 position is described as gamma v tau as the timed component. As the x position component, it's negative v tau, negative v gamma v tau. And the y and z are just 0. It's not changing along the object is not changing its position along the y and z direction with respect to the observer. Now, one thing we can do is to check how the tau is changing from here 0, 0, 0 to gamma v tau negative v gamma v tau 0, 0. So what's happening here is from tau, it's transforming into gamma v tau. This means the following. The time that's measured in the object rest frame as tau now becomes tau times gamma v. So there's a prefactor or multiplication factor of gamma v that comes into picture. And since gamma v is 1 over square root of 1 minus v squared, and v is always smaller than 1, which is the speed of light, then gamma v is less than, sorry, gamma v is larger than 1, because the denominator becomes less than 1. So 1 over something less than 1 positive, you get a number larger than 1. So this gamma v tau becomes larger than tau. This means the following. Time dilates in the reference frame of the observer that's moving with a velocity v with respect to the object at rest. So we have shown using this 4 position, and starting from the 4 position for an object at rest, and applying the Lorentz transformation TV on this 4 position, we found that the time is dilated, meaning that the time that ticks in the clock of the object at rest is going to be different than the time that ticks in the observer frame. And since if this is measured as tau, this is measured as gamma v tau, larger than tau. So the observer running at velocity v is measuring the time at a slower speed. So the time actually ticks slower. Let me give you a physical example. Suppose there's a radioactive element, and it's decaying, and it has a lifetime of, say, tau 1/2. Okay, and then according to this observer, the measured half-time of the object will be half-life of the object will be gamma v tau 1/2, which is going to be larger than the half-life of the object when it's at rest. So the objects that are moving at a certain speed will measure the half-life or the decay time of some material longer. This could be taken the other way around as well. If you are at rest as an observer, but the object is moving with a speed, again, we expect the object to decay slower according to us. So this is the time dilation, and this is how one can actually find it from starting by the 4 position for an object at rest and applying the Lorentz transformation. Thank you very much for listening to me. Please subscribe to my channel if you would like to watch more videos, upcoming videos. Thank you.